recording. And the first thing I want to do is talk about Wednesday and Thursday, which is the midterm. And I want to share with you my screen on Canvas. And it looks like you're seeing it. This is the assignments page, okay? And at the very bottom, you should see midterm 1 and then midterm 2, which is the current midterm. And it has two parts. I was almost able to find everything I wanted in WebAssign. There was one problem that I couldn't find. Okay, so it's worth 4 points. It'll be just like a worksheet. You download the worksheet PDF document, and I'll show you where that is in just a second. And then you have to upload right here. See, it says a file upload, so you can go ahead and upload the file right there in the assignments page. Part B that's just instructions that say complete midterm 2 part B in WebAssign. There are 10 problems in WebAssign, okay? And they're fairly short. I picked the shorter problems, but those are worth 24 points. And so the total exam is worth 28 points, and there are 11 questions, okay? And they're not equally weighted. Obviously, if you got 10 problems and it's worth 24 points, some of them are 2-point problems, some of them are 3-point problems. The one that you're going to do on paper, that is worth 4 points, and that's only because you have to show your work. And so I'm weighting that just 1 extra point more for that single problem right there. I can tell you that one is a pair production, pair annihilation problem, the one that you're going to do on paper. And so you'll upload it just like you would have on any other worksheet. And you'll do the problems in WebAssign just like you've been doing homework in WebAssign all semester. Notice they're both due Thursday night at 11:30, and they will be open. The ability to start doing the problems in WebAssign, or to download the one problem that's on a PDF document. That'll happen on 11:30 a.m. on Wednesday morning. So you have 36 hours to finish the exam.
Professor?
Yeah, part A right there says
it's
due at
yeah,
11:30
it's
a.m.
due at 11:30 a.m.
That's a mistake. Okay, good. I'll fix that right now. I'm glad you guys are awake. It defaults to odd things at times. And so let's change that to 11:30 p.m. That's when it's due. All right. And hopefully then I have to remember to save it, which is probably why it was wrong, is because I probably forgot to hit the save button at the end. All right. So let's go down there. All right. AM, PM now, PM. Both of them are due Thursday night at 11:30. All right. How do you find the one problem that's on a PDF document? Go to modules. And right after syllabus and schedule, which it decided to open, is midterm 2. And these are the same 2 assignments. For whatever reason, when you're over in modules, it doesn't give you the due dates, but it should have changed that, just like, 11:30 p.m. you can see is the due time. But the file itself, go to modules, back to modules, not to assignments. The document itself will be right there. And that isn't yours. Okay, that's one I used a couple of years ago. But of course, you'll find the rules. I'll even throw some equations and constants probably in front of it. You download it, you work the problem. Here's some other problems I've used in years past, but none of those are a pair production, pair annihilation problem. The correct file will be there probably sometime this afternoon, but you won't be able to look at it until Wednesday morning. Okay, I'll lock the folder so that you can, and lock the file so you can't open it up until Wednesday morning. By the way, if you're worried about why that is, if that concerns you, one of the things I have found, and it's unfortunate because to some degree you guys are being punished for your predecessors. I think I gave about 2 or 3 days to do a final exam in the spring semester. And what I came to find out was there was this thing called Chegg System Expert Solutions. They take about a day or so to turn them around a little more. And because I'd given so long for my students to do the final exam, they were able to submit the questions on the final exam to a Chegg expert in order to solve it. And I was grading exactly the the same solutions as the Chegg system expert, because I was able to get a password and log in and see those exact same things. I should just tell you, you know how I caught him? The expert made a mistake, and 4 of my students made the exact same mistake. It was just an algebra mistake. So unfortunately, I can't make the exam longer like I might like to, because that allows people to submit questions to Chegg to be solved by a person. And obviously, I don't know how anybody could believe that is legal. You know, the exam rules say that it's open book, okay, but you can't work with another person. And if an expert solves a problem and you copy it, well, that's clearly not your own work. Okay, Chegg is specifically a prohibited website. You can use anything that's up on Canvas. You can use your book. You can use your notes. Any of the worksheets I've given you, and I will post my solutions to the worksheets on Canvas as well. You can use any of those things. You can't work with anybody else, and that's kind of the rules. All right. Any questions on the midterm?
This exam that you're on right now,
Yeah.
it's posted on Canvas just as like a placeholder.
This is a placeholder. Yeah, it
Okay.
actually was an exam too for a previous year. Okay, any one of those questions could be good questions, but they're not the one that you're going to have to solve. So this is exactly right, a placeholder, and the right one will show up here probably this afternoon, but you won't be able to see it until Wednesday morning. Okay.
Got it.
Yeah.
Thank you.
Yeah, I just wanted to get something up there so I can show you where it'll be when you go, and it'll be in modules. Close up syllabus schedule. Right there, the right question worksheet, the right question sheet will be sitting right there. And then these are the 2 places that tell you to go do parts A and B. All right, so I'm going to stop sharing that. And let's see, where were we? We were working with Schrodinger's time dependent wave equation, which, if you think about it, allows us to figure out these things called wave functions. The symbol is psi. And once we have psi, the 2 things we learn to do with psi, this wave function, is first to normalize it, because we want the area under the wave function everywhere to be equal to 1. That means that there is a probability that of 100%, 1.00, that the particle that is represented by the wave function will be someplace. And then if we just take that wave function, actually I should be more careful what I'm saying. It is actually the wave functions squared, the wave function multiplied by its complex conjugate, that we integrate over all space, and that has to be equal to 1, because that thing, the wave function times its complex conjugate, is called a probability density. Okay, and so that thing integrated over all possible values of x has to be equal to 1. And so then if we want to know what the probability of finding a particle in a particular region of space, all we have to do is integrate that particular region of space, like maybe from x equal to 0 to x equal to 5. We want to know what the probability of finding a particle is right there. We just do the integral. If we went everywhere, it'd be 1. So if we want to just go from x equal to 0 to x equal to 5, that'll be the probability of finding a particle in that particular region of space. And that's Born's interpretation of quantum mechanics. The thing we were working with, though, and I want to start sharing my notability screen with you, is we said, well, you know, this time part about the Schrodinger's time-dependent wave equation. All right, let's do our screen mirroring. All right, look, it's working today. I always like when it works. What we've talked about, go away, come on, yeah, go away. All right, what we said, and I hate my handwriting when I look at it here, but for these wave functions, when you multiply by its complex conjugate, it is guaranteed that will always go to 1, okay? The part of the wave equation that is a function of time, when you multiply by the complex conjugate, will always multiply to 1, because e to the minus I omega t multiplied by e to the plus I omega t gives you e to the 0, and anything to the 0 power is just 1. Guaranteed. In this particular example I was doing right here, the space part, the part that was a function of x, also went to 1, but most often it won't. Example today, we'll do the infinite square well problem, and you'll see the space part doesn't always go to 1. So it would be handy to have a version of Schrodinger's time-dependent wave equation that is independent of time. It hopefully is a simpler differential equation to solve. And that's the motivation for what I had started to do on Friday. Of course, ran out of time because in upper level physics classes that often happens. And that was, we had started with Schrodinger's time-dependent wave equation. And we were hoping that we would be able to come up with a version of that that would eliminate the time derivative and simplify the equation to solve in other cases. And we were going through a procedure that mathematicians have found tried and true. And that is, you assume that your overall answer, the capital psi, can be broken up into 2 pieces. One piece that is only a function of position, and I choose, like most textbooks do, to have that be the lowercase Greek psi, which is only a function of position. And then you multiply that by just any function. And I just went with f here, a function of time, also being, these two are multiplied together. And so we're saying that that is equal to the overall wave function, which is a function of both position and time. There's an assumption there, and it's well-founded in how the physics turns out in the laboratory to verify. Okay, it's not just some pretty math theory. It works. This happens when you do experiments on this stuff. But that's our opening assumption. And so what we do, and I'm in this ugly purple here, I'm talking about the steps that we did on Friday. You take this thing and you plug it right in there, and right in there, and right in there. Okay, and you simplify as much as you can. What I mean by that? Well, see, when I plugged it right in here, I realized that the derivative was with respect to time. And so the space part, the part that is only a function of x, is constant with respect to time. And so it slides right by the time derivative, just like any other constant would. On the other hand, and there's a mistake here, that's a second derivative right there. Over here, it's the time piece that is a constant with respect to the derivative. So it slides right by when I took that second derivative. Of course, both pieces show up right there. So that's always step 1 in this process, which is called separation of variables. Our goal here is to separate the time part on one side of the equation and the position part, the x part, to the other side of the equation. Well, you can see I kind of got a mix on the left here. I got position x and time f of t, which is a function of time and a time derivative. So the solution next is to divide through by psi, the thing that is only a function of x, and f, the function which is only a function of time. And I do that everywhere, and say here, I just did it and it's missing, right? Okay, what cancels? Well, the psi cancels right here, which is only a function of x. The f function, the f of t function, cancels right there. And I think I've achieved our goal, which is to separate things. On this side, over here on the left, everything is either a constant or a function of time, a derivative with respect to time. Over here on the right, everything is a function of x or a derivative with respect to x or a constant. And hopefully you can see over here, that's only a function of time. There's a time derivative. That's a function of x. That's a function of x. And it's a second derivative with respect to x. By the way, these potentials that we're talking about, they have to be a function of x as well. Now, I do want to point out a little notation. In most introductory courses, U is the symbol for potential energy. For whatever reason, when you start taking upper level physics classes, potential energy is written as V. The units of both are joules. Okay, so don't let this become voltage or potential difference like it often does in electricity and magnetism. Stay with U or V as meaning the same thing. It is potential energy in joules. And the example I'm going to do here for you in a little bit, hopefully will clear up exactly what sorts of things you might find in this term right here. Okay, but here's the math theory. The mathematicians maintain that it is impossible to come up with a function f whose time derivative and a function psi whose second derivative with respect to position will be equal to each other when multiplied by these fairly random constants here, okay, and have an additive thing over on the right side. It's impossible to find two such functions in all of mathematics. And it's a theorem that it is provable to show that, but I think it would be reasonable. Think of like a sine and a cosine or some kind of polynomial. It just would not ever work, okay? With one exception, and that's a constant, because of course the derivative of the constant, a derivative of some function is equal to a constant, a derivative of another function is equal to a constant. That could be the only possible solution. And so that's what the assumption is here, that we're going to say the left-hand side is equal to a constant and the right-hand side is equal to a constant. And that's as good as we can do, because the left-hand side has to be equal to the right-hand side here. All right, mathematicians will prove that for you at some point if you force them to, but I've accepted it as reasonable. You know, I can't think of any two functions, f and psi, whose second derivative with respect to position and whose first derivative with respect to time multiplied by a bunch of random constants could possibly satisfy that equal sign right there. And so I'm willing to stipulate a constant is the right answer. Okay, so at that point then, I'm going to look at the left-hand side here, and that's something I can solve for you. And the right-hand side, we're going to call that the Schrodinger time independent wave equation. It's a simpler version of Schrodinger's wave equation because we've completely eliminated time for it. But now we have a differential equation we can solve and hopefully come up with the space part, psi of x, which will allow us to get probabilities of finding particles in particular locations, because we would just take that space part and multiply it by its complex conjugate. That would be a probability density. We would probably have to normalize that thing in order to make sure that the area under that curve is 1 everywhere, and then we could predict probabilities of finding that particle in particular locations. But I have to make some conclusions about the left-hand side. And so I gave myself a little bit more paper here to work with. And that's what we're going to do here. I hate this kind of purple color, so I'm going to go back to my kind of normal blue. And I'm just going to rearrange this thing a little bit. Okay. Is there a mistake there that I see I'm missing? And I think the answer is yes. Can anybody see it? I see it now that I'm looking to go work on this equation. What happened to this guy right here? And this guy right there on Friday. I was rushing through a little bit on Friday, but see that there was still a 1 over f left over, just like there was a 1 over psi left over on the other side. Okay, so if you're following along here, please fix that, because it's an important step. And I was rushing on Friday at the end of the period, and now that I've had time to fix it, I can see that there's clearly a mistake there. But I want to solve that equation. Okay, and it is perhaps with differential calculus and integral calculus the one differential equation that you can actually solve, because you just integrate in order to solve it. And it's called a first order linear differential equation. First order because it's a first derivative. That's what the mathematicians mean by first order. Linear because nothing is squared here, particularly the derivative. Okay, there are second order equations. They'd have second derivatives, and sometimes they're squared, and so they're not linear. But this one you can solve. And here's what I'm going to do with it. I'm just going to take that thing and I'm going to manipulate it a little bit. And I'm going to drop the fact that I was writing partial derivatives, because right now the left side there is only a function of time. So I don't need partial derivatives anymore. And what I've got is df dt and then I got a 1 over f here. And I'm going to bring the constants over to the other side of the equation with that b. So it's 1 over h bar times b. All right. Nothing wrong with that. I think it's more conventional to bring I up into the numerator. And so the way you would do that is multiply by I over I. So I have I over h bar, and I times I is a -1. And so that's what I'm going to write. Okay, the next step I'm going to do, if everybody's happy with that, is I'm going to multiply by dt. So then I've got df over f is equal to minus I over h bar times this constant b, which some people refer to as the separation constant, times dt. All right, I've kind of cleverly moved things around here. So if I integrate this thing, okay, and I'm going to integrate it from, I don't know, we're going to drop the arbitrary constant. So I'll just do an indefinite integral, okay? I think that most people would believe this is the natural log of that function f is equal to minus I over h bar times the separation constant times time plus a constant. All right. Well, I'm going to insist, and if you want a more rigorous proof, I'd probably have to come to office hours for it. We're going to let that go to 0. Okay. We just do. And it really is, there's a reason for it. You know what? Let's keep it. Let's keep it as a constant. I won't make it go to 0 right now. I can handle it, and you'll see where it shows up. So I'll go plus a constant, because the next thing, I mean, it's an indefinite integral. There really is no great justification other than it's going to work to throw it away. But in order to solve for f here, the next step has to be to exponentiate both sides, right? So I'm going to go exp of both sides. And of course, the exponentiation of a natural logarithm, those are inverse functions. So I'm left with f over there. And over here, I'm left with, and I'm going to write e as opposed to exp, minus I over h bar times that separation constant times time. And then I'm going to write it like this, plus e to the c power. And hopefully you realize I've made use of the fact that the exponents, when you're multiplying, these exponents just add. And so all this is another constant. And so essentially I'm saying the function f as a function of time has to be equal to this constant right here. We'll call it a, as we often do, e to the minus b over h bar and multiplied by time. Now, in the examples that we've worked so far, the time, oops, what have I dropped? There is a mistake there. Everybody see it?
I.
I dropped the I, absolutely. I dropped that I, didn't I? Just like I dropped that F earlier on Friday. Okay, so I guess the question though is, what do the units of this thing have to be right here? Okay, the units of an exponent have to be dimensionless. I can live with radians, I suppose. And time is clearly going to be in seconds. So this thing B over H bar, it has to have units of radians per second or inverse seconds. It has to look just like omega, doesn't it? Well, we've said that energy, which is equal to H times F, or is equal to H bar times F, times omega, well, that must mean omega is equal to E over H bar. So this B here, this separation constant, it has to be the energy. And our value for F, our function for F as a function of time, must always be some constant E to the minus I omega times T. Always, always, always. There's no other solution you can have for the timepiece. And then the overall wave function is equal to the lowercase wave function, which is only a function of x, times e to the minus I omega t. Now I've dropped the constant here. It is more conventional to put the constant in with the wave function that's only a function of position, as opposed to with the function of time. So I've absorbed it in here, and then the process of normalization will reveal what that constant is. And so back up here where I was thinking of just throwing away this constant right here, what I'm really doing is saying it gets absorbed into the solution for psi as opposed to the solution for f. And hopefully that's acceptable. Now, what's left? Because that's the time independent Schrodinger wave equation. Now that we've decided that this constant here, B, is total energy, I can rearrange that thing in the square block right there. And I'm probably going to have to slide up and down a few times in order to get that right. But I think what we were left with was E, because that's the constant B that we need. We just showed it had to be, the constant is the total energy, was equal to minus, and I keep wanting to drop that negative sign, so I was careful not to do it here. I looked at my notes, times 1 over psi times the second derivative of psi with respect to x plus the potential. And I think I've got that. I've got the negative sign, that's a positive sign, that's a positive sign. The more conventional way people write this is, all right, what happened to my pen? It just turned off. Of course it did. Multiply by this guy right here, the energy times the wave function, which remember is only a function of x now, is equal to minus h bar squared over 2m times the second derivative of psi with respect to x plus the potential energy times the wave function. And again, the wave function is only a function of psi. This guy right here is referred to as the time independent Schrodinger wave equation. If you solve it, it should reveal for you what the wave function is. If you want the total wave function, you always just have to multiply by e to the minus I omega t. But remember, that piece will always be irrelevant according to Born's probability argument, because anytime I find this, which is the probability density, it will be exactly the same as this, the solution to the time independent wave equation, because e to the minus I omega t times e to the plus I omega t will always go to e to the 0, which is just 1. And so it's a little bit easier to solve this equation than solving for this guy in the total Schrodinger time dependent wave equation. And so that's what we do. All right. Any questions on that? It's a nice little compact equation. When people say they're doing quantum mechanics, more often than not, what they're referring to is they're solving this equation right here, perhaps the most famous equation in quantum mechanics, Schrodinger's time independent wave equation. All right, moving on this worksheet, I just want to show you something. Okay, I would like to do this problem right here. I don't have time in order to do it today. So what I'm going to do is I'm going to solve this problem in a little video, and I'd like you to watch it before class on Friday. I've assigned it in class to other sections before, and it's a pain in the butt from a calculus perspective. So I'll show you how it works. But the point is, now that I have Schrodinger's time independent wave equation, right? And I got to go minus h bar squared over 2m, second derivative of psi with respect to x plus the potential energy times psi. Now that I have this thing, I can put it there. I can put its second derivative right there. I can put it right there. I should be able to solve for what the potential is. And in this particular case, the particle is in free space, so that's equal to 0, so that term just goes away. I can figure out what the potential energy is that has this as its wave function. And I'll tell you what the result will be. It is going to be a function that looks just like that. Okay, it'll be a quadratic function, which hopefully you would recognize as a simple harmonic oscillator. Okay, because this is one of the wave functions for a simple harmonic oscillator. We're sort of doing that problem backwards. Look to the video to see how it gets solved with all the gory mathematical detail, but that is the point. More often than not, that isn't the way quantum mechanics works. Instead, what we work from is some sort of potential energy function, V, and we work the problem the other way. What is the corresponding wave function, lowercase psi? Okay, and that's where I want to go to next. And I'm going to move on over to, where did it put it? Not 101. That's one of the things I haven't figured out about Notability is how it organizes documents. I'm sure it has an order here that it believes is correct. There it is. It put it right up top for me. Okay, and I want to talk about potential energy. And in this particular graph, I'm using U, which is what we did in PHY211, and you probably worked with Dr. Tech in 111, PHY111. But now that we're in modern physics, for whatever reason, we've changed the symbols on you. We mean V. Okay, and you can see a potential energy curve, just an arbitrary one. Okay, plotted as a function of position. Just pulled it out of a book somewhere. It's a great looking picture. What does it mean? Well, it means nothing in and of itself until you also plot on the same curve what the total mechanical energy is. And in this case, we're even given a numeric value, 5 joules. Well, that seems to mean that if you're a particle right here, you're kind of trapped on this side because you don't have enough kinetic energy to overcome the potential energy well that you're in. However, if you are trying to get out this way, you have plenty of energy over here. And in fact, I think this difference here between total energy and potential energy, that would be the kinetic energy the particle would have out in that region over there. Okay, everybody's followed me so far? Because total energy, mechanical energy, is equal to the sum of kinetic energy plus potential energy. But now we're calling the potential energy V because we can. I think my next slide is going to say exactly that same thing. The difference between the total energy and the potential energy is just kinetic energy K. And so right here, you'd have 1 joule of kinetic energy if the particle was to try to move to the right. But if it tries to move to the left, it can't get past that point right there. Okay, it doesn't have enough energy to exceed the potential energy trap that it is in. Okay, keep going there. What if I only had the total energy equal to this, I guess that's a black line right there? Well, now the particle is trapped in between that region right there. It can't get out of this potential energy well at all. Okay, it can't escape from that point. Okay, if I had a total energy equal to 3 joules, the I guess kind of pink line right there, if the particle was over here, it would be trapped on the left well. If the particle was over here, it would be trapped in the right well because it couldn't get past those points right there. It just would not have any kinetic energy to allow it to get out. Okay, and if you went with the green, well, then the particle would be trapped at x2 right here and unable to escape those positions. All right, and so what do we say about the Schrodinger wave equation? Okay, and I can see right here, anybody see a mistake in the first, and I looked at it, and just because I've been writing it, I see clearly I have an error. There should be a negative sign right there. I've tried to drop that negative sign over and over and over again throughout my physics life. Okay, and what we did though is we took a separable solution, put it in here, here, and here, and we came up with the Schrodinger time independent wave equation. And we showed that that is what the timepiece always is. And so our goal then is to figure out what is that guy, the other piece. Okay, what is that thing right there? And so here's an example following from what I just said about wells, but let's draw a well that's the simplest one you can possibly imagine. And it's called a square well. It's an infinite square well. And by that, I mean, outside of x equal to L or x equal to 0, the potential extends up to infinity, right? And so there is no amount of total energy this particle can ever have that would cause it to be able to come out of that region between 0 and L. Here's how the potential energy function can be defined. Okay, it's infinity here and it's infinity here. And conveniently enough, we decided, because you can often put the 0 potential energy to be any place you want, we put it 0 joules inside the well where the particle is trapped. And that's what we're going to take into Schrodinger's time independent wave equation. And I see I haven't written it on this slide here, so let's do that. So we said that E times psi is equal to minus h bar squared over 2m times the second derivative of psi with respect to x plus the potential energy times the psi times the psi. Well, that's Schrodinger's equation. Inside the well, that term is 0. Nice, easy problem. You can see why we pick it as the first one to do. And so what I'm left with then is the other parts right here. And all I've done is do a little bit of mathematical rearranging here. I solved for the second derivative, which means I multiply by 2m over h bar squared. I've got that E right there times psi. And what we're going to do is we're going to define that grouping of terms there to be k squared. That says k squared is equal to 2me over h bar squared. Okay, just redefining, mostly because we're lazy physicists, it's too much to write that. Why not just write k squared? Now, that may seem like an odd thing to do. Why not k to the first power? It turns out that in acoustics, a guy by the name of Helmholtz had solved this exact equation multiple times for things like standing waves on a string, for example. Okay, and so the solution to this equation right here, just bringing the minus k squared to the other side of the equation, was well known. It had been solved. Fourier had a hand in it too, but Helmholtz is the guy who gets credit for this equation. In fact, this equation that I've got the circles on right here is known as Helmholtz's differential equation. Mathematicians in the 1800s had solved it. Okay, it also tells me that the value of k would just be the square root of all this, right? And the solution to this differential equation, well known by Helmholtz and all the other scientists of the day and mathematicians of the day, is sines and cosines. Okay, how do you prove that that's the solution? Well, I'm asserting it, but of course, if I was to take the second derivative of this thing and plug it right in there, and take the thing itself and put it right in there, well, if it answers a differential equation, which I think it will, you know it to be correct. Okay, it meets the requirement that when plugged in here and here, the equation is solved. Okay, and just a quick, we'll use a quick notation. Think about the fact that the first derivative of a sine would just be a k cosine of kx. I guess the derivative of that cosine is going to be a negative sign. No, not that thing. Minus bx sine of kx. And then the second derivative would be equal to a k squared. Now, derivative of the cosine is minus the sine of kx. And then the derivative of the sine minus b. All right, why did I write x right there? I got no idea why I wrote x right there. It should be bk. And so now it'll be bk squared, chain rule again, derivative of the sine is plus cosine of kx. And so I've solved this side. And notice, isn't that just equal to minus k squared times psi, which is the other side of the differential equation? Just factor out the k squared, and you're left with k squared times psi. So this thing that I put a box around is the solution to Helmholtz's differential equation, a math equation well known in the day. And I guess my proof is that I took that second derivative. All right, so now, what things do we have to do? There's my Schrodinger's equation with the fact that the potential is equal to 0 right here, plugged in, okay? That's my rearranging, that's what K must be, and here is my wave function. I think there are some conditions we talked about on Friday. We know that there is 0 probability that the wave function can be out here. I don't want to write that. I want to say this. Erase that. I want to say that out here, psi star times psi has to be equal to 0. The wave, the particle is trapped, is what our discussion, in this area right in here. And same thing over here, psi star times psi out here has to be equal to 0. The particle can't be out there. There is no probability that it could escape. And so that means two things. The wave function when x is equal to 0 has to be 0 at this side. And the wave function on the other side, when x is equal to L, also has to be equal to 0, because we're not allowing for discontinuous wave functions. Okay, they have to be single valued. So if outside of this well, the wave function has to be 0, because when multiplied by its complex conjugate, it has to be 0, then right at that point, the wave function has to be 0 right at the boundary on both sides. Okay, well, if I go in and I say, well, at x is equal to 0, if at x equal to 0, the wave function has to be equal to 0, I think I put x right there. Well, the sine of 0 is 0, so that's good. But the cosine of 0 is 1. This side goes away. And so b times 1 has to be equal to 0. The only way that could be true is if b is equal to 0. And so the wave function becomes a times the sine of k times x. We basically take this term and we say the cosine doesn't meet the boundary condition that the wave function be 0 at the two edges, at x equal to 0 and at x equal to L, this infinite well that the particle is trapped in. Okay, so it has to be a sine function, and that kind of makes sense. That's what a sine function looks like. Or you can think of a next one, bloop, bloop, bloop. Sines look like that, right? They could conceivably have zeros at the two edges. But this far edge here has some issues, right? Because if I need this to be 0, a times the sine of k times x to be equal to 0, when kx is equal to k times L, well, that only happens when k times L is equal to an integer multiple of pi. If you think about what a sine curve looks like, where is the sine curve hitting the zeros? Well, at 0, at pi, at 2 pi, at 3 pi, at integer multiples of pi, k times L has to be equal to an integer multiple of pi in order that the sine of k times L be 0 at this far boundary here. Okay, so all of a sudden, k sub k is quantized, we would say. It's there's multiple places, multiple values of x, I guess, where the wave function will go to 0, one of them being x equal to L, but there's a whole bunch of different ways that can happen. N could be 1, could be 2, could be 3. 0 would be kind of trivial, wouldn't it? So we're going to exclude n equals 0. Think about why that is a little bit. But we already said that k had to be equal to that, didn't we? And k simultaneously has to be n pi over the width of the well. Well, that allows us right away to solve for what the energy is right there. The energy is, I guess, square it. So that squares the n, squares the pi, squares the L. And then I guess I just multiply, no, what do I multiply? Square, then I have to multiply by h bar squared and divide by 2m. And sure enough, I get what the energy is for each of these states being n equals 1, n equals 2, n equals 3. And if this reminds you of the standing wave on a string experiment that I know 7 of you did in PHY211, well, that's not an accident. It's supposed to. Okay, the wave function here is supposed to be exactly the shape of the standing wave on a string experiment, and each wave function has a particular energy given by this equation right here. All right, let's plot those. I'm going to jump to one of the problems, okay, in the worksheet for today. And this is, where is the worksheet? Okay, it's got all my 101 stuff. There we go, infinite square well. And I'm going to skip this because that tells you, okay, we've just got this equation, just solved it. We solved Schrodinger's wave equation, perhaps for the first time in your life, okay? Remember I said we would put the constant, it could have been with the timepiece right there, and this is capital psi, and I just found the equation from the previous slide, a times the sine of n pi x over L, and I slapped on what we've been calling f of t right there, and I've got the full wave function. The first step is going to be to normalize it. That is to say the integral from x equal to minus infinity to x equal to plus infinity of that thing squared, a squared sine squared n pi x over L, which is k times x, times dx, because when I go psi times psi, that thing just goes away. That has to be equal to 1, and that will allow me to figure out what the constant a is. Okay, I'll hold on that. And then once I've got that constant a, if I want to figure out what the probability of finding the particle in a particular location, and I just decided between there and there, well, that probability would be equal to the integral from 3L over 8 to, and I've just picked 5L over 8. So that's, if you look at the well, that's 1/8 either side of half, because there would be L over 2. And so I'm going, okay, go an eighth back and an eighth back. What's the probability that the particle will be in that range right there? And so I would go a squared, once you know what the value is from normalizing it, times sine squared of n pi x over L dx. That would be the probability that sits right there. Now, I want to draw some pictures. I'll finish solving this problem on Friday, and you're going to do a problem similar to it before Friday that I'll talk about in just a second. But let me move on to, oops, I didn't want to leave there. Let me move on to the rest of the story here, which is graphing these things, okay? And so here I've drawn the well, and I've said, let's say that that is the energy for the n equal to 1 state, okay? And remember what the energy is for these various states. And I think I decided, do I have it written down here? Yeah, let's see if I can wing it by memory here, which is always a dangerous thing. There was an n squared out front, right? There was a pi squared, there was an h bar squared, and there was a 2, whatever the mass of the trapped particle is, times the width of the well squared. There's L right there, okay? And what we're saying in this problem is when n is equal to 1, okay, this particle has 4.3 EV. And then any other energy for n equals 2, n equals 3, n equals 4 equals 5 can be found from that. But I want to think about what the wave function looks like. What does the sine, some amplitude, which has to be normalized to be found, sine of n pi x over L look like when, for example, n is equal to 1? And I think the answer is that. Okay, that's the sine with one loop is what we would have said in the standing wave on a string experiment. Let's go over to n equal to 2. So now n is equal to 2, and hopefully you can see that the energy, if this guy was 4.3 eV, what would the energy be for this particular mode? Well, the energy would be 2 squared, 4 times 4.3, somewhere around 16, 17, yeah, 17.2 is the energy of the second mode, 17.2 eV. This should remind you a little bit about the Bohr energies, right? The Bohr energies had that minus 13.6 eV, and then every other energy was actually divided through by n squared in that case. In this case, it's multiplied by n squared for an infinite square well. But what does the wave function look like for this n equals 2? I think it looks like that. The second mode of a standing wave on a string. All right, I've got to finish up here because I'm keeping you 2 minutes early. Let's think about n equal to 3. N equal 3 would have an energy, let's see, 3 squared 9, 9 times 4.3 eV. So the energy of the third mode would be, multiplied it out, 38.7 eV. And what would it look like? The third harmonic of the standing wave on a string experiment. Okay, and I think that would be this function right here with a 3 sitting right there in place of the n. Okay, if you want to graph those yourself to prove if I'm graphing them right, feel free. I'm fairly confident here, but here's the point. We were looking at what is the probability that the particle will be found, oh, right in that region right there. Well, what do I have to do? First, I have to square these things. Okay, so I'm going to swap on over to my my PowerPoint where I left off. Okay, there's my wave functions. If I square them, I get that picture right there, and I've shown what I've been plotting on these energies right here. The question is, I guess, what is the probability that the particle is right there, near to 1/2? Well, it should be a pretty high probability. And you can numerically get it using the process I showed, normalize to find A, and then integrate from, in the case of just an eighth before halfway and an eighth after, I can get that area. But what do you think would be the probability for the second mode of finding the particle right in that same area near the center? Pretty low, huh? Because that area right there is pretty small. There's a greater probability that it'll be near the center for this next mode here because there's some area under the probability density curve, which is psi squared. That's quantum mechanics for the simplest possible problem we can come up with. You find by solving Schrodinger's equation what psi is. You square psi by multiplying by its complex conjugate to get psi star psi, which is a probability. And then you can integrate over areas in order to find what the probability is that the particle will be in a particular point. And remember, before you did that, you had to ensure that the probability anywhere where the particle can be is exactly 1, a process we call normalization. All right, 5 minutes over on you today. I'll hang around here for a little bit. If anybody has any questions, the one thing you have to do in addition to the homework, which is due on Friday night, midnight, is if you go to worksheet It's coming, it's coming, it's coming, it's coming. Worksheet 24. Come on, you can open up here. You can do it. What I need you to do, all right, where is it? Where is it? Where is it? We've done all these. We've done all these. I must have the wrong worksheet. Worksheet 25. There it is. Worksheet 25. What I need you to do is this problem right here, number 2 in worksheet 25. And notice it's slightly different from the problem we just did because it's a cosine there instead of a sine. And notice the well isn't 0 to L, it's minus L over 4 to plus L over 4. So it's similar to the problem we have to do. You have to do 2 things. You have to normalize it to find A, and then you have to find the probability that the particle is in that region right there between 0 and L over A, okay? So those are the 2 questions. A little bit of calculus keeps everybody sharp for Friday. Questions? Sorry, I'm taking so long. Yep, go ahead.
That's due Friday, and we submit to Canvas, or we have it ready to present.
I'm going to have you upload it. I want to watch you do some calculus.
Okay, before
right.
Just by Friday.
Yeah, by Friday for class. We'll talk about it in class on Friday, and we'll continue on with the infinite square well come Friday as well. Okay. All right. Good luck on the exam. If you have any questions for me, let me know. Send me an email, and we'll try to straighten everything up. But hopefully, it'll be very similar to the first midterm, and everybody will do well. All right. Hey, I got to let you go because some of you probably have to go off to class, but I will be here if you got any questions about anything we've done. I'll hang around for about 15, 20 minutes for office hours. All right. Have a great day. Talk to you guys later.
Thank you.